Good evening, welcome. My name is Jesse Mason, and tonight I'm going to give you guys a guided tour of the most incredible images I think we have access to on the planet, the Hubble images. Before I get started, I'll say a little bit about myself and then about the Hubble Space Telescope. I went to school here. I should say I went to school there when that was a high school. And in the summer of, I think it was 97, there was a very, very strange object in the sky that captured my imagination, and I became fascinated with astronomy. I'm talking about a comet. This is the Hale-Bopp Comet, and I would see it frequently, pretty much nightly, and it sort of sparked my interest in astronomy. I came to the library and I checked out a book on constellations, and this is the first time it's come home. I think I calculated the fines. At the time it was 10 cents a day. We're looking at something like 20 years worth of fines. So my speaking fee doesn't even come close to covering the fines on this book. I actually just talked to the front desk and they said I have to buy it now. So I'm going to be buying this book and reinstating my parents' membership and my family's honor. And my interest in astronomy continued in college. I started out studying music, but eventually I found physics, and that captured my interest as well. And along with it, I came back to astronomy, and I currently work at Oakland Community College running their physics and astronomy labs. I teach part-time at Eastern Michigan University. I teach physics there. And recently I started an astronomy club. I gave this talk first a little over a year ago to an audience in Farmington Hills, and the response was so overwhelming I decided on the spot that I was going to start an astronomy club. And anybody who wants to sign up, they can give me their email address. And now we have an astronomy club in Farmington Hills, and we do a monthly star party out there. Tonight, after the presentation, the skies are clear enough, I brought a telescope, and I will take you out, and I think we talked about it. We're going to meet just to the, I guess it would be the north of the library. So as you walk out of here, if you take that sidewalk down to Maple and hang a left, right as you get to the exit, I'm going to say it's a high school exit because I forget what it is now. Is it a middle school? The middle school exit. There's a flat area. I'm going to set up a telescope there, and I'll give you guys a tour of the things that we can see from that spot. So any questions about me, first of all? By the way, so if you have questions, I will be answering them to the best of my ability. I will tell you that I am a trained musician. I am an astronomer as a hobby and a passion, but I don't know everything about it. But I do stay up late at night reading about it. Okay, with further ado, this is the Hubble Space Telescope. The Hubble Space Telescope was launched in 1990, in April of 1990. It just celebrated its 25th year. And that 25th anniversary last year was the impetus for me to do this slideshow. It all starts with this gentleman. His name is Lyman Spitzer. In 1946, he published a paper about the advantages of having a telescope in space. And the advantages, namely, are that it has increased angular resolution. The reason we enjoy having a telescope in space is because down here on Earth, we have this atmosphere, which is, to astronomers, kind of like looking up through a swimming pool of water. It's very wavy, and it's the thing that gives the stars their twinkle. And if you're trying to do advanced astronomy, it's very challenging. So if we could put one in orbit, we would get rid of those atmospheric disturbances. And additionally, we would have access to super optical vision. Our atmosphere absorbs infrared radiation and ultraviolet radiation rather well, and if we could get a telescope up there, we would be able to observe those types of electromagnetic radiation as well. So in 1965, this gentleman heads a committee on creating a space telescope, and in 1968, the funding is approved, and they began construction. The idea was that it would be done by 1979. Unfortunately, we had an economic recession, and that caused the funding to kind of go up in the air, and the project got canceled. It was reinstated in the late 70s with a projected launch date of the early 80s. but because we had many different companies working on the project, there were setbacks in time and budgets, and most of the companies were asking for more time and more budgets. Eventually, they got it launched in 1990. But before doing so, they renamed the telescope from the Large Space Telescope to the Hubble Space Telescope. And why did they do that? They did that for the gentleman that's smoking a pipe. That's Edwin Hubble and his friend Albert Einstein there looking through a telescope. Edwin Hubble made a really incredible discovery in the 1920s. We were trying to figure out whether or not the Milky Way was the only body like it, the only island of stars in the universe. And to figure out if it was, we had to figure out the distance to these other curious objects that they called spiral nebulae. He sort of springboarded off some work by a young lady named Henrietta Leavitt, and her work showed that certain kinds of stars, we called them Cepheid variable stars, those stars fluctuated their brightness in proportion to their true brightness. And because we know how light dims with distance, this gave us a way to measure the distance to these certain stars called Cepheid variables. If it's clear enough tonight, if the light pollution is not too bad, I might be able to point out the namesake for the Cepheid variable, Delta Cephei. It's a star that varies in brightness in the constellation Cepheus. And when I say it varies, it doesn't actually vary to a degree where you can observe it with the naked eye over a period of a night. But if you watch these Cepheid variables, you could see them varying over a long time. Anyways, at the top right of the screen, we have what he thought was a nova, which he crossed out with an N when he realized it's a variable. And this nebula, we called it the Andromeda Nebula. Instead of being the perceived tens of thousands of light years away, it was moved back to 2.5 million light years away, which put this nebula way outside of our galaxy. And shortly after, we accepted the idea that this, in fact, is its own galaxy. And I'll show you a better picture of this as the slideshow goes along. In addition, we discovered that these extragalactic galaxies show redshift. That's a way of saying that they're moving away from us. And some other observations revealed that the further away these galaxies are, the faster they're moving, which tells you that, which prompted him to propose what we call the expanding universe hypothesis, that our universe is expanding. And subsequent observations confirmed this theory, and it's pretty well accepted now that the universe is expanding, not only expanding, but now at an accelerated rate. And if you rewind the clock, that's where we get the idea of a Big Bang. So here's the construction of the Space Telescope. What you're looking at is the primary mirror. Tonight we will have a mirror that is 1 foot across. This mirror is about 8 feet across. It's a very large aperture. What I want you to think about is how your eye works. You have a pupil that lets in light. Your pupil is anywhere from 3 to 5 millimeters, and by increasing it to this size, you're becoming something of a giant, and you're able to see a ridiculous amount of light. The specifications of the creation of this mirror were very, very strict. In fact, there was a problem with it. I'll get into that in a second. But the specifications of this mirror required that it would be ground within 1/800,000th of an inch. And to give you an idea of how big that is, if we scaled up this mirror to the size of our planet, the variation in elevation could only be 6 inches. So it's a very, very strict tolerance we had. So here is the Hubble Space Telescope making its way on April 24th, 1990. And this is the Hubble Space Telescope being deployed. The entire telescope is about the size of a school bus. Fits tightly into the shuttle bay that you see here. There it's being released. A diagram of how this sort of telescope works. Light comes in. This is going to be how our telescope works tonight. or at least similar to it. Light comes in and bounces off a primary mirror and off a secondary mirror, and then it's collected by instruments. Usually a telescope has a secondary mirror throwing the light out the side to an eyepiece, but this one goes back through the center, and the instruments are back there. So this is a comparison between ground-based imagery and space-based imagery. You can see an improvement in the resolution. The planet Pluto and its moon Charon. Here's the Hubble Space Telescope version. And we won't get to see it this nicely tonight, but hopefully we'll have a chance to see Saturn tonight. This is the Hubble Space Telescope image of Saturn and the Hubble Space Telescope image of Orion Nebula. This is the window curtain structure in the Orion Nebula. Now, these images are incredible, and if I remember correctly, my dad had a book on astronomy that I grew up with, and these images were in it. But they were very underwhelming compared to what the people that worked on the Space Telescope were predicting. And in fact, it was very underwhelming to the public as well, because by the time the telescope was created, they had spent over $1 billion on the telescope. And there was sort of a public outcry on this. Eventually, a team of engineers and physicists, and maybe even a few chemists sprinkled in, came up with a solution. They were going to give Hubble corrective optics. In other words, they were going to give Hubble a monocle. And they designed it to telescope from the instrument bay into the in front of the primary mirror. And 3 years after the Hubble was put in orbit, they launched COSTAR, Mission COSTAR, which stands for Corrective Optics Space Telescope Axial Replacement, carried to space on the Space Shuttle Endeavour. And there's some astronauts installing COSTAR. Also, while they were up there, they boosted Hubble's orbit. Anything that's in orbit, contrary to some belief, actually does hit some atmosphere. The atmosphere is really thin there, but it does encounter some drag, and eventually its distance from ground decreases. So they boosted Hubble's orbit while they are up there. In fact, every time they went up and did a repair mission on the Hubble Space Telescope, they boosted the orbit. They are done doing so, and we expect Hubble to, unless something happens, burn up in the Earth's atmosphere in 2035. I'm very optimistic, though. I hear that they're thinking about selling it to a private investor or a series of investors that would purchase it for private use. And if they do so, they'll keep Hubble up there for many years to come. The replacement that we're expecting to go up there in a couple of years is the James Webb Telescope. And though it has astronomers drooling because of the specs and the discoveries that it's likely going to find, it is not an optical space telescope, so all the images it returns are going to have to be false-colored for us to enjoy. Hubble, however, takes mainly optical images. What you see is sort of what you get. So here is what pre-COSTAR looks like, and this is post-COSTAR. The resolution is seriously increased, and every mission since then has improved the resolution. So we're going to be seeing a smattering of images tonight from throughout Hubble's tenure in space. So that window curtain structure I showed you guys, I'm going to show you the new version. Better resolution, better contrast. I'm going to zoom in on this curious object and tell you a little bit about stellar formation. This is what we call a propylid, a proto, which stands for a protoplanetary nebula. This is what we think a star and its planetary system looks like when it's being born. A star is born when a large cloud of gas and dust collapses in on itself due to its mutual gravitation, and as it does so, pressure and temperature go up, and at a critical point, fusion takes place. It starts fusing the hydrogen that it has into helium, and if there's anything left over of the nebula, they turn into planets. Some of them don't make it into planets. They'll just become something like an asteroid belt or perhaps a Kuiper belt. I'll say more about those as we get to them. But this is what we think a baby solar system looks like. So that Orion Nebula comes from the constellation Orion, the winter constellation Orion. We're not going to see it tonight because it's not up. Orion is probably the favorite target of amateur astronomers. In its sword lay a gorgeous nebula. It is probably the most incredible nebula in our sky, and it has certainly taught us the most about stellar evolution. It is the Great Orion Nebula. So I'm going to show you a ground-based image of the Great Orion Nebula. If you know anybody that's into astrophotography, they may have an image that looks like this. A beautiful image, but with the Space Telescope, we get something that looks like this. So what is the Great Orion Nebula? The Great Orion Nebula is what we call a diffuse nebula. It is a nebula of gas and dust that is, we believe, currently forming stars. So in a way, this is a stellar nursery. We believe hundreds, if not thousands, of stars are being born in this particular stellar nursery. And I won't show you, I'll back up just a few. If you could see the entire Orion Nebula complex, so they call it the Orion Molecular Cloud Complex, it would cover the entire Orion constellation. It's an enormous cloud, but the central star formation is taking place on the Great Orion Nebula. Our star was born in a nebula like this, and it had sister or brother stars, if you will. But since then, our star has lost its companions, and this is what happens to what we call stellar clusters, or open clusters. They eventually get torn apart by gravitational interaction with other objects in the sky. So I'm going to zoom in on the central part of the nebula. We're going to refine the image just a little bit. I'm going to show you what they call the trapezium. If you have a decent telescope and you're looking at the Orion Nebula, you can actually see the trapezium with an inexpensive telescope. But before I do so, a comparison of the size of this nebula. This is the angular size of our moon compared to the nebula. So it's a very large nebula. By the way, this nebula is 1,300 light years away, which makes it even more impressive. A very, very bright nebula for being so far away. To give you some ideas of size, when I say 1,300 light years, that is not a near Earth object. That is significantly far away, but it's still within our galaxy. In fact, every nebula you see is going to be from within our galaxy, except for one. So this is the Trapezium Nebula viewed in optical. I'm sorry, the Trapezium cluster viewed in optical. And this is the Trapezium viewed in infrared. Hubble images in infrared as well as optical. So I talked about stellar birth, and I talked about our sun just a little bit. To give you an idea of the size of our sun, I've got a series of slides here to paint the picture of where our sun falls in the stellar evolution. We'll start out with some planets that you might be familiar with. Mercury on the left, Mars, Venus, and Earth. Venus and Earth very similar in size. Now we shrink Earth down to be that size so we can fit the rest of the planets in the panel. And to give you an idea of volume here, if you wanted, you could put 1,000 of Earths inside Jupiter. I'm hoping we can see Jupiter tonight. It depends on our horizon, if it's blocked by any trees or whatnot. Yes, sir? The moon? Yeah. Oh, it's very large. We're talking about light years in size. When I say angular size, I'm saying when you look at it in the sky, if our moon was in the telescope view of this, that's the size of the moon compared to that, yeah. It's much bigger. Our solar system could probably fit inside of this tiny little spot right there. So from Jupiter, we'll move to the size of our sun. So we shrink Jupiter down, and you can see a size comparison of our sun in Jupiter. This is a red dwarf, and this is the brightest star in our sky. This is the winter star Sirius. It's about 8 light years away. It's extremely bright. That's why it's extremely bright, is because it's 8 light years away. It's not only slightly bigger than us, it's really close as far as cosmic distances are concerned. So we shrink Sirius down, and you can see some of the larger stars. These we call red giants. Arcturus we're going to see tonight. That's a really cool star. And we shrink Aldebaran down, and then we get to some real giants. We call these supergiants. Antares we'll see tonight. Betelgeuse, or Betelgeuse as it's more correctly pronounced, is on the opposite side of the sky. You see that in the winter in the constellation of Orion. So we shrink Betelgeuse, and this is where it lies with the largest stars we know. These panels are actually a little outdated. I think these are 2 or 3 years old. We've found 1 or 2 stars that just nudge VY Canis Majoris out of the running for largest stars we know. This is a star I'm hoping we can see tonight. This is a really cool star. I shouldn't say cool, it's pretty hot. It's a very, very large star. Canis Majoris, if you placed Canis Majoris where our sun is, it would swallow Mercury, Venus, Earth, Mars, and Jupiter in its surface. It is an enormous star. And to give you an idea, here's a pixel that represents the sun. You can't even see it here. There's the limb of the star. There's the sun. If you take a Boeing 747 and you get in it today, leave Detroit Metro, and you take the longest path possible around the planet, nonstop, if there's a way to refuel midair, how long would it take you? About 2 days. 2 days is about how long it would take you. If you nonstop, no bathroom breaks. If you got in that same Boeing 747 and you tried to do that on the sun, it would take you 200 days. 200 days nonstop to get around the surface of the sun. If you attempted to do that with VY Canis Majoris, it would take you 780 years. A very, very large star. Curiously enough, just because it's large doesn't mean it's massive. It's only about 17 times the mass of our sun. Size doesn't necessarily translate into mass with astronomy. And just to tell you or show you where this resides, this star resides in this nebula here in Canis Majoris, the dog constellation. So some other nebulae. This is what we call a reflection nebula. The gas and dust is being illuminated not like these overhead lights here. They're not fluorescing. These clouds of gas and dust are actually just reflecting the light from these parent stars. This is a famous cluster of stars that you can see with your bare eyes in winter. It looks just like a smattering of stars in a very tight space to the right of Orion. They call these the Seven Sisters. Does anybody speak Korean? The Pleiades cluster? In Korean is pronounced Subaru. And with your naked eye, that seventh sister is really hard to see. So when you see Subaru logo, you'll see that there's only 6 stars there. This is about 400 light years away for us. And it's about 100 million years old, this nebula and cluster is. Which in terms of clusters is actually pretty old. Usually an open cluster like the Pleiades is torn apart within a couple tens of millions of years. This one we call a dark nebula. The surrounding diffuse nebula is illuminated, but dust is in the way, and so we see this dark nebula. Does anybody know what this nebula is called? Any guesses? It's the Horsehead Nebula. It's the Horsehead Nebula. And this one is in the Orion molecular cloud complex, somewhat near to the Great Orion Nebula. And so here we go. We're all going to take a deep breath, and we're going to blow away the clouds of gas and dust. Ready? 1, 2, 3. Good job. So what you're looking at here is an infrared image. Infrared allows us to dive deep into these clouds, which is why the Juno mission, which just reached Jupiter, has infrared capabilities. It wants to peer through the clouds of Jupiter. Here, the Hubble Space Telescope is peering through the clouds of the Horsehead Nebula and telling us a little bit about the structure on the inside, where the densest part of the nebula is. And this is, by the way, this is a good explanation of why the James Webb is going to be an infrared telescope, because it can tell us a lot more about what's there than optical. So, by the way, this image, of course, is false colored because we can't see infrared. This is a beautiful nebula called the Cone Nebula. And if you have a small telescope, you can catch this cluster of stars, and you can see why they call it the Christmas cluster. It looks kind of like a Christmas tree with all the different colors and the stars there. This one was not colored. No, this is a true color image. So this is kind of a creation of a gentleman that took an existing image, maybe several images, and some data about the cloud structure, and he created a three-dimensional model of it to represent what you can't really see. And that you can see what's presumably the parent cluster of this cloud illuminating, reflecting over here and illuminating over here this nebula. This is the one nebula that you can see outside of our galaxy, and the reason is it is incredibly luminous. This is the Tarantula Nebula, which exists in the large Magellanic Clouds. In the southern hemisphere, you can't see it from up here. In the southern hemisphere, you can see these big puffy clouds in the night sky. And those puffy clouds exist outside of our galaxy, but they're nearby. And inside of one of them is the Tarantula Nebula, and it is the most active starburst region, that is, stars being born, in our local group of galaxies. It is ridiculously bright. To put it in perspective, if we took the Tarantula Nebula and we put it where the Orion Nebula is, which is 1,300 light years away, this is 160,000 light years away. If we pulled this to where the Orion Nebula is, you could read by its light at night. It would cast shadows on the ground at night. This is a very, very luminous nebula. Probably 500,000 suns are being born in this nebula. And if you see it just right, you can see why they call it the Tarantula Nebula. It has these appendages that are very similar to the arachnid for which it's named. Well, astronomers can see that at least. I think this should be called the Brain Nebula. They call this the Crescent Nebula. It's another emission nebula. You have a parent star that's lighting up the cloud of gas and dust around it. And this one is actually undergoing a shock wave. You can see the two different types of clouds, and one is kind of bursting through the other, fluorescing it as it goes. This is a gorgeous image of the Gabriella Mistral Nebula. I have another picture of this that's less impressive, but that shows you why they call it the Gabriella Mistral Nebula in black and white. This is a Chilean poet that won a Nobel Prize, and maybe a Chilean astronomer discovered it, but that's why they call it that. Striking resemblance. This is called the Handsome Devil Nebula. I've heard there's a resemblance. This is the Eagle Nebula. I always have a hard time seeing the Eagle Nebula, but I'm told that the beak is here, and like the wings kind of go up like that. Looks like the beak of an eagle. These are perhaps, or I should say, this is perhaps the most adored nebula by Hubble workers, because when they put CoStar in, the image of this nebula, and I'll show you. This is an Earth-based photograph, by the way. This is the Hubble photograph. This is the image, and I'm going to show you the close-up, that they revealed after they put the lens on Hubble and said, we got it, it's under control. And this is the image they released. And they retitled this The Pillars of Creation. What you're looking at is a 4 light-year long pillar, several pillars, undergoing star formation. Incredible image. To put it in perspective, our solar system could fit easily inside that little tendril right there. On top, you have these little spires that are kind of spitting off things. We'll see that more in a little bit. But that is evidence of star formation as well. This is called the Trifid Nebula, also an Earth-based image. I want to show you that compared to the Hubble image of the nebula. We're going to zoom in on this structure up here because it's really interesting. We're going to boost the color contrast just a bit. I shouldn't say boost it. What they actually do is Hubble takes a green color image, a red color image, and a blue color image, and it takes those and it combines them, and when it does so, this is the result. So these little things sticking off this little part of the nebula, they call them evaporating gaseous globules, or eggs. And what's going on there is there's a nearby star that is radiating an ultraviolet, and that ultraviolet is peeling away the less dense parts, revealing the more dense parts. So we believe that inside of these eggs, there may be a star on its way to forming. Appropriately name eggs, then. Here's another one of those three-dimensional images by this gentleman. This is called the Heart Nebula. You can see how the cluster inside is kind of pushing the gas, radiating it away from the cluster, leaving only the densest parts there. And this one was released, I think, in the last year or two. They call this one the Mystic Mountain. I wanted to get a poster of this and put it in my bedroom, but my wife won't let me. I think it is a gorgeous image of star formation. The Mystic Mountain is actually a part, I think it's this part right here, of a giant molecular cloud complex called the Carina Nebula. It's about 10,000 light years away, and it has two of the most luminous stars in our galaxy, and I'll show you one of those in a little bit. But an incredibly gorgeous nebula complex. So this is what I hope we can see this tonight. It all depends on light pollution and seeing conditions, whether the atmosphere is really turbulent or not. But we might be able to see this nebula. This is what happens when a star like ours is on its way out. It goes through a series of gas, I don't want to call them explosions or burps, but they exhaust gas from their surface, and then they push it outward, and that gas, after these events, it leaves behind a different sort of star. They call them a white dwarf, and those white dwarfs illuminate the nebula, and typically they're the most beautiful objects in the sky, and I don't think we've ever found two that are alike. I should say, are at least the same. They are very unique, and I think it's really cool that every star as it goes leaves behind its own stellar footprint. This is called the Ring Nebula, and if you see it through my telescope tonight, it's going to look something like this, maybe a lot smaller. It's going to look like a faint, dusty Cheerio, but this is what the Hubble Space Telescope sees. You can see the parent star right here. That's the white dwarf that's illuminating this nebula. It's about 2,300 light years away, pretty far, about a light year across. And the different colors are due to different gases being fluoresced. This is another image, a more recent image showing a little more detail, going back to that one. This is a more recent image by Hubble. And the most recent by Hubble is probably the most beautiful of all. It reveals earlier stages of gas exhaustion. So the most recent being the closest, and that being the farthest away. This is another planetary nebula. They call them planetary nebulas because when they first found them, I'll go back to that first ring, when they first found them, the astronomers figured what they were seeing was planets forming in the sky. They thought this was going to be a Jupiter someday or something. And it wasn't until we got better measurements we realized that those came from stars. And so this is the nebula that actually came from the fainter of those two stars. They call this the Southern Ring Nebula. You can see this in the southern hemisphere. This is an almost perfectly spherical shape. This one doesn't have a unique name. It's just named after the astronomer that found it, Abel 39. And only about 20% of planetary nebulas have a spherical shape. This is one of my favorite because you can get sort of this kind of structure through the telescope on the ground. It's called the Eskimo Nebula. Kind of looks like somebody wearing a parka. These outer spokes that you guys see here are quite unusual for a nebula. But the parent star here is like our sun. So this is what our sun could look like when it goes through its dying phase. You don't have to worry, that's about 5 billion years away, so we've got time to plan. This is called the Rotten Egg Nebula. They call it the Rotten Egg Nebula because this particular nebula has a high concentration of sulfur. Sulfur, viewed in yellow. The blue, I believe, is oxygen and nitrogen, but that yellow is sulfur fluorescing. That sulfur towards the parent star is moving at a rate of 1.5 million kilometers per hour. And it's causing a shock wave, which is what's fluorescing the nitrogen and oxygen. Some call this the Boomerang Nebula. I prefer its alternative name, the Bowtie Nebula. The second image is actually an image of the first one that's been polarized, and I should say that's false colored to show the polarization of light, to show you that there's something interesting going on here with the polarization. Another nebula, they call this the Butterfly Nebula. You can see the parent star there. This is showing this binary lobe. They think that inside this nebula, there used to be two stars. I should say before this nebula was created, there were two stars orbiting each other. Many of the stars you guys see in the night sky are actually two, and we'll see a couple of those tonight through the telescope. Occasionally, they do more than orbit. They collapse in on one another, and when they do, they can go through this phase of gas exhaustion and become a totally different star. And the star they became is a red giant. The Bug Nebula. This is one of the hottest spots in our entire galaxy. One of the most complex nebulas we've ever seen. This is a really cool one, the Twin Jet Nebula, because we actually have observed it long enough to have different images of it, and I strung those together in a GIF movie, and you can see how they rotate. What you're seeing here is the precession of the nebula, or perhaps the precession of the star as it illuminates the nebula. These bipolar nebulae are, we believe, created when the cloud is, or I should say when the star is exhausting gas along its poles. Here's another one, another bipolar planetary nebula. We believe there might be a binary star system in the center of this. We're not sure. Many times the binary systems will survive, but as they're in there, they will exchange material and send it hurtling away from the binary system at incredible speeds. This is one of the most famous nebulas. It was on, I think, was it National Geographic? I think it was National Geographic. And the title was God's Eye Staring Back. This is called the Hourglass Nebula. Cat's Eye Nebula. This is cool. We have a close-up of this one. And other telescopes, such as the Chandra telescope, can actually take ultraviolet and sometimes X-ray images. This is an X-ray optical composite. So this is the same nebula taken with X-ray, I believe using the Chandra telescope. So that's optical. That's X-ray and optical put together. So every wavelength telling us something a little different about the stars. So in 2002, this star was observed doing something bizarre. The nebula surrounding it seemed to be expanding, and they discovered that it wasn't actually expanding. What they were seeing was what they call a light echo. So the star did some kind of brightening. We don't know exactly what happened, but it did some kind of brightening, and that brightening was seen throughout the nebula as an expansion. And so what I'm going to show you is a series of images where it looks like the nebula is expanding. It's not really. It's just the light is illuminating different parts of the nebula. And of course, this light is traveling at light speed. So this is what we're seeing, is this seeming expansion of this nebula at light speed. That's the final image I think we have of it. Looks familiar to some. Don't know if that's where they got their inspiration, but it looks really close, doesn't it? This is another light echo. They call that a light echo. This is a movie of a light echo in a southern constellation called Puppis. These variations are the variations I was telling you about. I think the period here is actually 40 days or so. This is a Cepheid variable, so that's kind of what a variable looks like as it's changing its brightness. Hard to believe what we're looking at here is 6,500 light years away. That is the kind of resolution Hubble has given us. I said that some of the most luminous stars in the galaxy are in the Eta Carina Nebula. In the Carina Nebula. This is Eta Carina, one of them. This is a hypergiant blue variable star. It looks like it's exploding. Most people will say it's exploding if they see this image, but it's not. That's actually just the nebula being fluoresced by the parent star over here. This nebula was formed by an outburst that put this star at, I think, the second brightest star in the nighttime sky when it created this in 1841. We expect this to go supernova soon. It turns out that stars with high stellar masses, that is something between like 5 and 10 times the size of our sun, instead of going through those planetary nebula phases where they kind of puff off this gas and illuminate it, sort of like a stellar gravestone, they just blow themselves apart, sort of like a out-of-control celebrity or something. This one will do that eventually, and when it does, it will be quite a bright star in our sky. In fact, I think we'll see it during the daytime. This is a star that is encased in a nebula. This one is also expected to go supernova anytime. This one's 20,000 light years away. Neither of those put us in danger. They're much too far away. I think you'd have to be closer than 50 light years for any concern. This is what they look like after they blow apart. Not much left. In 1604 AD, this star went supernova, and when it did, you could see it during the daytime for about 3 weeks. And then Kepler discovered, using a telescope, Kepler discovered the clouds remaining here. By the way, to put a supernova in perspective, we really didn't believe it when we started seeing the evidence for these things. A supernova, when it goes, it outshines the entire galaxy. I'll say that again because it's so hard to believe. Like, a galaxy is comprised of hundreds of billions of stars. When a supernova goes, it outshines all of those stars. It puts out more energy than our sun puts out in its entire lifetime when it goes. It's a remarkable event. Another one of those great 3D images. This is another supernova remnant. You can kind of see the spherical shape to it. We believe this is about 5,000 years old. We caught a supernova in 1994 in the act of going. That's this one right here. But even better, I'll show you an image, or a series of images of a supernova going. This one we caught last year. So over the course of weeks, we see a part of this is a galaxy, of course, we see a part of this galaxy fluoresce and exceed in brightness. It doesn't look like it might not exceed the core of the galaxy. It exceeds most of the rest of the galaxy. This is a galaxy that's about 80 million light years away. This type is called a Type 1a supernova. There are a couple different types. This is what's left over sometimes. This is what we call a pulsar, and you can see why we call it a pulsar for obvious reasons. Believe it or not, this is a slow motion image of what's left over in the center here. They call it a neutron star. This neutron pulses, and so we call it a pulsar. And the reason it pulses like this is because the radiation coming from the star only comes out its north and south poles, and it's spinning so rapidly that it flashes like that. And if you're in the way of those flashes while that star is spinning and precessing, it looks sort of like a lighthouse like that. And this is the Crab pulsar. This is a slow motion video, so it actually rotates 30 times a second. And what's rotating is about a 15-mile wide, dense, I should say super dense, leftover star. They call them a neutron star, comprised entirely of neutrons. This pulsar belongs to this nebula. In the night sky, in the winter night sky, you can see this with a telescope. This is the Crab Nebula. We can zoom in and see some of the fine structure, the filament structure. Zooming further in, you can see why they call it the Crab Nebula. Through X-ray, we can see the Crab Nebula through a whole different lens. You can see this swirling mass of gas surrounding this central exhausting neutron star here. And in this next slide, you see several different types of stars, low mass stars like our sun, combining hydrogen to become helium. The larger the star is, the more complex the core becomes. And so this is an image really of stellar evolution here. In supergiant stars, you have all sorts of element creation going on. And if I'm going to mention the elements, I have to put this up here. Though I did really, really struggle with chemistry. The first four elements, we believe, were present even before the first star. But it was the first heavy stars that created elements 5 through 12, so all the way through magnesium. And we believe that supergiant stars can create these heavier elements all the way up to iron. But everything after iron, including some elements that are in the human body, they only come about through supernova. And so there's this great quote by Carl Sagan, "We're all made of star stuff." But I like a better, more hands-on approach. If you hold your hands up in the air, everybody do this. Hold your hands up in the air. There is likely, astronomers will tell you, it is likely that you have material in your left hand that came from a different star than the material in your right hand. You have different stellar materials in your body right now. Even in your two hands, come from different stars. And sometimes stars rove in a pack. These are two tightly packed clusters. This is a famous cluster that I might be able to get through the telescope tonight called the Perseus double cluster. It's just kind of a chance alignment of these. We don't believe they're gravitationally bound. But two very beautiful, somewhat old, we think they're on the order of 10 million years or so, clusters. And both are heading right at us. They will take a really long time to get here. This is a different cluster, and this we will definitely get to see tonight. It's the most beautiful what we call globular cluster in the nighttime sky. This is a cluster that exists around the halos of galaxies. We believe around the Milky Way there are somewhere between 50 and 150 of these objects. They are comprised of hundreds of thousands to millions of stars in a very tight space. In stellar terms, this one's about 150 light years across, and it's about 25,000 light years from here. To put 100,000 or a million stars in 150 light years would be ridiculous. To put it in perspective, if you were on a planet in the middle of this globular cluster, when you looked at the night sky, pretty much everything you would see is stars. It would completely be daytime. There would be no such thing as nighttime in here. This globular cluster is kind of famous because in 1973, we pointed a really, really big telescope at it and we sent it a message. The message contains stuff like the structure of our DNA, the evolution of our species, maybe even some music. I can't remember, but we sent that in 1973, and in 25,000 years, well, in 25,000 years, this will have moved a little bit, but as I understand it, the core of this will still be relatively in place there. In 25,000 years, maybe some alien species. We really doubt now that there are any intelligent life in globular clusters because of how the stars form and how we believe planets form and life zones and whatnot. But if there were something there to receive it, they would receive our message from the Arecibo telescope. So remember this, we're going to get to see this. I can zoom in on this because it's such a gorgeous cluster. Again, this is an image from the Hubble Space Telescope. Hundreds of thousands of stars here. Our closest star, by the way, is about 4 light years away. That is to say, light takes, at its incredible speeds, it still takes 4 years to get to our nearest star. The average separation between stars in a globular cluster is about a light year. And at the core, it's only about 100 Earth-Sun distances. This is another globular cluster. You can see this in the southern hemisphere called the Omega Centauri globular. It's the largest globular in the Milky Way. We believe there are about 10 million stars here. And another interesting thing about the globular clusters is that they predate our galaxy. We believe our galaxy is predated by these clusters by hundreds of millions of years. So this particular cluster, we believe, is about 10 billion years old. And our current, by the way, our current estimate for the age of the universe is 13.78 billion years. So these are really, really old stars. This is a close-up of the Omega Centauri Nebula. You can go even closer. It's ridiculous how many stars you got. We can go even closer and boost the color contrast. I take that back. My notes say this is real color contrast here. This actually brings out an interesting aspect of these globular clusters that until recently we didn't understand very well. The blue stars weren't expected to be in globular clusters. As we sort of date the clusters using the red stars, and the temperatures of the stars are what gives them their color. And just like in our experience here on Earth, the hotter it is, the bluer it is. The dimmer it is, the redder it is. Now, the thing about hot blue stars is they require immense amount of fuel, and so blue stars, they tend to burn up within a few million years. Our sun has been around for 5 billion years and will last another 5 billion, we believe. And the blue stars, they only last about 10 million years or so. So how come in this globular cluster, 10 billion years old, we're seeing stars that only last about 10 million years? And the answer, we think, is collisions. Two old stars crash into one another, creating a high mass, high fuel consuming star that radiates in the blue part of the spectrum. And so all these, they call them blue stragglers because we didn't figure it out until recently. All those blue stragglers, we believe, are results from stellar collisions. By the way, are there any questions? Yes?
The little white ones, they're stars?
Yep, Every little dot you see there is its own star. And now we're hunting for exoplanets, planets outside of our solar system, and what we're finding is that nearly every star we find has planets. And so I don't know how long planets could exist in a globular cluster. I don't think it would exist very long. So I probably would say there's not many planets in this cluster, given how close they are. Yes, sir?
What is causing the globular clusters to coalesce?
Just as my understanding is just gravitation. Gas clouds form stars. Immense gas clouds form large bodies of stars. And the globular clusters, we believe, just kind of clump together. A better question, I shouldn't say a better question, but a question that asks about something like this. What gives this its shape? Like why globular clusters are spherical, right? These tight little packed spheres. They don't seem to show much interesting shape or distension. The spiral nebulae like this one, this is the Andromeda Nebula. Now we call it the Galaxy because we know it's a galaxy. You can see this, by the way, on a really dark night in a dark place in Michigan with your bare eyes. It looks something like this. It's remarkable. But through the Hubble Space Telescope, this is what we get. An incredible image of what we now believe is 1 trillion stars. What gives this its shape? And they're still debating what gives spiral galaxies their shape. Some of the recent discussion involves this new exotic matter we call dark matter. We still don't completely understand it, and it's still debatable about whether or not it's, I shouldn't say it's debatable. Most people are starting to accept the idea it's there because the way those spiral galaxies rotate, they don't seem to obey Newtonian physics. And the easier explanation than creating new physics is to say, well, there's just something there that's making them behave in a way that that we're observing. In other words, in typical spiral galaxies, we would think that the stuff that's closer to the center would spin faster because of the greater gravitational force to the core. But in these spiral galaxies, we're noticing that the entire galaxies are rotating sort of like a record, almost like it's fixed in place. That doesn't make sense from a Newtonian physics standpoint, nor does it make sense from an Einsteinian physics standpoint. And the current explanation is that surrounding all galaxies is a halo of dark matter that is exerting a gravitational force on the galaxy itself. Hard to substantiate something you don't see, though. So let me tone down your expectations. You are not going to see this through my telescope tonight. You won't see anything like this. In fact, if we're lucky, you'll see something that's more like this little smudge. What we'll see is probably this bright central core. You really need dark skies to see any of the shape out here. And of course, this is a Hubble Space Telescope image of the Andromeda Galaxy. And it's got a dwarf galaxy companion. We have dwarf galaxies. That's what the Magellanic Clouds are. But we believe that the Milky Way is slightly smaller than this. So when the two do contend, the Andromeda being one of the few galaxies that's not moving away from us, this Andromeda Galaxy is moving right towards us. It will be on us in 5 billion years. So when the sun goes, we'll have another thing to worry about, the Milky Way and the Andromeda doing battle. And when they do, we believe the Andromeda is going to win because our current estimate is that the Andromeda has 1 trillion stars. In the Milky Way, only 400 billion, I believe. We'll see if either of them survives with the beautiful spiral shape. But we have a long time to wait, and in the meantime, we have a great view of this. This is 2.5 million light years away. It is the furthest thing from us that you will see tonight if I can get it through the telescope. But when I do, just remember, it's not that the visual that should be impressive, but it should be the idea of what you're looking at. You're looking at the light of 1 trillion suns. And I use the word sun intentionally. Sun denotes a star that has planets around it. And we believe that in galaxies, unlike globular clusters, nearly all the stars have planets. I think the current ratio is nearly all the stars have planets, and 5% of them have Earth-like planets. So what does that give us with 1 trillion suns here? That gives us, I believe, 50 billion Earths in that galaxy. Yes? That is the farthest thing you can see with the naked eye. Yep. Yes?
Could Hubble see behind and further beyond
Like
the cluster?
behind the galaxy? It can't pierce the galaxy, no. I believe with infrared, I take that back. I have never seen the Hubble infrared photos of this. So maybe with infrared it can see behind it, can see through those dust lanes, but I've never seen it. What it did do recently, and I think they released it last year, is Hubble took a very small part, I shouldn't say a very small part, it took like a quarter of the galaxy, like a chunk like this, and it did a high resolution image. Because, I mean, this is really impressive, right? You're looking at this blur that represents a trillion stars, but you still just see like dust, just like our Milky Way. When we look up at the Milky Way in our sky, it just looks like dust. It's not until you get a pair of binoculars on it, it really does, all it takes is a pair of binoculars to start to make out individual stars. A large part of that dustiness is because it's just many, many stars. So anyways, Hubble went back and re-imaged the Andromeda Galaxy, just a portion of it, and what they came up with is this image. Oh, not this image. Sorry, size comparison. If you could see it with your bare eyes, that's how big the Andromeda Galaxy is. It's something like 4 or 5, maybe 6 full moons across. This is what it saw. Somebody put this together from a PBS special, I think. So there's the portion of the galaxy that you see. Again, when it goes back to this, each star, each dot here is a star. And if you go online, you can actually download this image. It's about 5 gigabytes to download. I don't recommend doing that. What you can do is just go online. In fact, this would be great. This is great fun. I do this when I'm bored sometimes. Google Andromeda Zoom. And they have an interactive image of this where you can zoom in on whatever portion you'd like, and what you find is this. That dust is not dust. They are individual stars, and nearly all of them harboring planets. In this image, there's 100 million resolvable stars. I run the physics and astronomy labs at Oakland Community College, and I have access to the budget and to some degree command of the budget. And we got a 16-foot poster of this made. And we put it in the hallway, and people trip when they're walking by because they get caught looking at it. And I get the question all the time, I think you asked this, is every one of those a star? And I finally printed a sign that said, yes, every one of those is a star. It's hard to believe. Yes, sir? I will. Yep. So this is another spiral galaxy, a beautiful spiral galaxy called the Whirlpool Galaxy for obvious reasons. 23 million light years away. You can't see this with your bare eyes, but a good telescope and good dark skies, you can catch this one. The bright regions, by the way, the bright pink regions are active star formation, we believe. And we used to think this is what our Milky Way looked like. It's funny because there's so many models that I have in my labs that say this is what the Milky Way looks like, and now we believe it looks a little different. I'll show you that in a moment. This is what one of those galaxies look like when you view it from the side. They call this edge on. This is called the Sombrero Galaxy. And this, by the way, illustrates why we have trouble observing the true nature of our galaxy's structure, is because when we look towards the center or away, we're looking through all of this dust, and it's hard to see through it. Hopefully the Webb telescope will help us with the infrared observation, but we've been struggling with it for many years for that reason. Another edge-on galaxy showing you that dust lane. This is part of a famous couple of galaxies called the Leo triplet. I think I might have an image of that. And it's hard to do these justice as we're just flipping through them, but each one of these has hundreds of billions to trillions of stars. And each galaxy seems a little bit unique. And also in the middle of each of these galaxies, we now believe, in the last couple decades, we've come to believe that they harbor what we call supermassive black holes. When when very massive stars go through their dying phases after they've blown most of themselves apart, and they remain just the dying ember of this giant star, sometimes that dying ember can be so massive that it starts to deform space in a severe way, to the degree where not even light can escape it, and that's where we get the term black hole. Inside of this galaxy, we believe there's a 70 million solar mass black hole. Same galaxy, infrared. This is not actually a Hubble image. This is an image from the Spitzer Space Telescope. You remember Lyman Spitzer was the guy that had the idea for a space telescope. Well, he's got a telescope too. They shoot an infrared up there. This is more like what we think the Milky Way looks like now. In the last couple of years, the data has suggested that we have a bar going across the middle of the galaxy. Don't ask me why. I don't think we know yet. But we believe that 2/3 of all galaxies are barred spirals, like our own, like this one. It's about 100,000 light years across, much like ours. If this was our galaxy, the sun would reside right about here. So we live on some spur along some arm about halfway out from the center of our galaxy. These are the clouds I told you about. They would be familiar to you if I was giving this presentation in Chile or something. These are the Magellanic Clouds. They're called irregular dwarf galaxies. They orbit the Milky Way. We don't know exactly what they are. Some hypothesize that they are actually smaller spiral galaxies that competed with the Milky Way and didn't survive. This is an image of the larger Magellanic Cloud taken by the Hubble Space Telescope. And here's a weird one. This is called an elliptical galaxy. And this elliptical galaxy is a super giant elliptical galaxy, about 50 million light years away. I can zoom in on that core, and you can see this very weird structure here. We believe at the core of this galaxy there's a black hole. And that black hole is swallowing matter that comes near it. And matter that comes near it but collides at high speeds with other matter can throw off radiation and sometimes particles. And we believe that this plasma jet is due to that highly energetic interaction at the event horizon of the black hole. This plasma is moving nearly at light speed, and it spans 5,000 light years. And at this zoomed in view, you can see kind of the shape of an elliptical galaxy. It just kind of looks like a bright blob, much more massive and populated than a globular cluster, but it lacks the flat shape of a spiral galaxy. We call this a flocculent spiral galaxy. I think this is maybe a galaxy. They call this Hoag's object. It's an irregular galaxy. I think what they think happened here is this one did battle with one face on, and the other galaxy kind of burned right through it and left kind of a bullet hole. Not sure, though. It's kind of a mystery still. This is called the Black Eye Galaxy. This is a weird one because the inner part is actually rotating in a different direction than the outer part. When something like that happens, our best guess is it hit something. We do know galaxies interact, much like ours and the Andromeda Galaxy will interact soon. This is an image of two galaxies that are starting competition. You can see one that was formerly a spiral being kind of pulled apart, and that's what they do when they collide. They interact gravitationally. They will eventually hit one another. When I say hit, It's actually, when you remember how far away stars are, like our nearest star, even though we're smack dab in the middle of one of the lanes of the galaxy, the nearest star is 4 light years apart. So like 2 galaxies doing battle changes the shape of the galaxy, but in terms of individual stars, it doesn't do a whole lot because for the most part, they don't touch. Maybe the cores do eventually coalesce, but stars themselves rarely touch. I guess it's kind of like taking 2 handfuls of sand and throwing it at each other from like a mile apart. More gravitational interaction between galaxies. Violent interaction between 2 galaxies. This is a galaxy bursting through another galaxy. This looks more like a galactic dance. Eventually somebody's shoes are going to get stepped on. More galactic collisions. Trillions of stars here. Another galactic collision. And now gets to the point where I'm going to show you a couple images of mini galaxies in one picture. This is a cluster of galaxies called the Hale-Bopp Cluster. Everything you see here that looks like a disk, there, goes there. There's one that's kind of on its edge there. Trillion stars here, trillion stars here, trillion stars here, here. Lots of galaxies. And this one is one of those weird elliptical galaxies with those weird shapes. Another cluster of galaxies. These clusters that I'm showing you right now are clusters that were discovered using telescopes on the ground. Just pointing them in places in the sky, and we discover, hey, there's a couple galaxies here. And further imaging, like with the Space Telescope, reveals that there's galaxies in the background. This is a famous cluster that you can get with an amateur telescope called the Cone Cluster. Another cluster, this is a famous one called the Fornax Cluster. We believe these galaxies are about 62 million light years away. Okay, so you see this a lot in pictures. You'll see these a gorgeous image, and then there's this star that basically photobombed the image. And the telltale is this spike, right? The cross spike. Those are called diffraction spikes. So if you remember how a telescope's created, this is the part where I wish I had a chalkboard. Light comes in and reflects off a primary mirror, and it bounces off and hits a secondary mirror. Well, the secondary mirror is in the way of that light coming in, and so it's suspended by cross beams. And when it does so, it creates this artifact in the image for really bright, really close objects. I shouldn't say really close, but close enough to do this kind of thing. They call it a diffraction spike. So these stars are not part of this cluster. They're really close to the telescope compared to those galaxies. They're probably on the order of tens of light years, maybe hundreds of light years away. So within our galaxy. So if you see this spike, you know it's within our galaxy. Are there any other questions before I continue? Yes, sir.
Are any of the colors here that go to the distance?
Good question. Good question. I don't know the answer to that question. I want to say I suspect it on some of these red objects. In some of the further images, you'll see the further they away, the redder they are. It could be. I would suspect it, but I'm not sure. Oh, yeah. I mean, the matter has to go somewhere, so they stick together for the most part, but what's left over typically doesn't look like a galaxy. I should say it depends on the kind of interaction. So in the instance where you have a galaxy that blows through the center, like when the Milky Way and the Andromeda collide, they're not going to look like, they're not likely going to look spiral anymore. They'll look like just like a leftovers of a galactic collision. But if the collision involves a galaxy or collection of stars that are much smaller than the other one, the parent galaxy, or the bigger of the galaxies, will survive just fine, like the Milky Way did when it gobbled up the Magellanic Clouds.
If I may
Yeah.
add something. One of the things that astronomers did when they first got their hands on supercomputers was do simulations of galactic collisions. And they have had lots of fun doing it in the years since. And hop on YouTube, just look up videos of galactic collisions. I guarantee you will find
Yeah.
dozens, if not hundreds of them, and some of them are just awesome. In part because there's so many pictures from, Hubble and other sources where they have like these structures that it's our shape, and they're like, well, how do you set that up? And so they set it up on a computer and they start crashing galaxies into each other, and they're like, oh, not like that. Well, then they try it again. So simulation is a big part.
And you make it sound like it's like a computer game you could download on Windows 10. Like he's talking about supercomputers, like ridiculous amounts of power to run these simulations. Because, so in physics, the two-body problem is the most familiar one, but as soon as you get a three-body problem, trying to track the trajectories becomes really problematic. And what we're talking about here is like the billion-body problem or the trillion-body problem. Enormous difficulties. But with advances in computing, they're starting to get better ideas of what happens after a galactic collision. And we believe now, I think I can lob this idea that the shape of these spiral galaxies are from early interaction between two smaller galaxies. So I believe we get that shape from an early collision that flattens it out and give it a rotation. Whereas these elliptical galaxies, I don't think, maybe that's an elliptical galaxy. It hasn't really collided with much yet, so it doesn't have that spin, doesn't create that friction that levels out the plane of the galaxy. I'm sure in the next 20 years we'll have a much better idea of those things. But so this one's takes a little bit of explaining, and by a little bit I mean a lot. Where do I start? I could talk about this one image for hours and hours because the physics behind what you're looking at is incredible. In 1905, a young guy who served as a patent clerk in Austria was doing mad experiments in his head. And these experiments he ended up publishing in papers that shook the physics world. And to put it in the right perspective, at the turn of the century, in 1900, we sort of figured we had most everything figured out. We had a few nooks and crannies to explore, but that the physical world had pretty much been sussed out. And along came this gentleman that made a ridiculous suggestion that turned out to be pretty accurate. And that is, well, he just challenged the assumption that the whole idea of space and time was a fixed canvas on which existence was painted. He suggested that maybe if you go faster, you experience space and time differently. And his ideas we now call relativity. Of course, I'm talking about the young Einstein. His ideas we call special relativity. They weren't really widely accepted because we didn't have a way to go really, really fast at the early 20th century. And so those were kind of brushed aside. What did attract attention was his ideas about the quantization of energy. And it was his ideas about the quantization of energy that won him the Nobel Prize. And those ideas eventually gave birth to a whole new field of physics we call quantum mechanics. But how mass interacted with space and time was something in 1905 when he published these papers that didn't take into account acceleration or gravitation. And so that's why he called it the special theory of relativity, because it was a special case where he wasn't taking those things into account. He didn't like that this theory was incomplete, and he spent the next 10 years struggling to incorporate gravity. And when he did so in 1915, his ideas revolutionized our understanding of reality. They weren't accepted right off the rip because they were so unusual. But the simplest way to describe the general theory of relativity is that an object with mass or energy deforms the fabric of space-time. And by the way, space and time he linked together and said they're one thing. And so that around a massive object, space is not just that objects are attracted to it, it's that space is actually bent. And so is time. And this idea was confirmed in 1919 when a solar eclipse was observed. Einstein predicted this possibility, but he didn't realize that we would have instruments sensitive enough to capture it. He suggested that light could be bent around a massive object, sort of like refracting it through a lens, only you weren't bending the light, you were actually bending space with the presence of this mass. The problem is you don't see this in everyday life because if you're standing there and your buddy's standing in front of you, you don't see stuff behind your buddy bending around your buddy, reaching your eyes. But Einstein said if it was massive enough, we should be able to measure it, but he didn't think we ever would. Well, 4 years later, during a solar eclipse, they noticed that a star measurably changed place. And that was the verification of his idea that was needed for science to come about to admit that maybe space and time wasn't fixed. Maybe it could be bent. Einstein's other predictions with general relativity were that supermassive objects like galaxies, by the way, Einstein was one of the people that were on the other side of the argument, saying there's only the Milky Way. The universe is static, has always been and always will be. He was very reluctant to accept that there are other things called galaxies and that they have their own constituents of stars. And the idea of expanding space was something he also struggled to accept as well. But he believed that if there was something supermassive, like this giant elliptical galaxy here, that light behind it could be bent into a shape where we would see concentric rings of light behind it. And so what you're seeing in this image is the result of a supermassive object deforming space to the point where we can see stuff behind it. So this is a galaxy that's probably really over here behind the galaxy. This red streak is probably a small red galaxy around here. The light was traveling towards, how do I say this? It was traveling down into the left, and it was bent around this parent galaxy here and distended it into this crazy shape. So all these stretched galaxies you're seeing, including this one they call the dragon's tail, all these stretched galaxies are evidence of the deformation of space by mass. That phenomenon, by the way, isn't limited to heavy objects. Everything, we believe, deforms space and time. It's only in the supermassive cases that we can find it to be measurable. By the way, I mentioned solar eclipse. That gives me a good point to say, take out your phones and put this on your phone. Next year, on August 21st, 2017, we will have a solar eclipse, a total solar eclipse, visible in the United States. How many of you guys have seen a total solar eclipse? Just a couple? I haven't seen one, so I'm planning on I think I'm going to rent an RV and head south. You can't see it in Michigan, so you're going to have to travel to see it. But it's pretty worthwhile, as the people who have seen them can attest. In the middle of day, the sun, I don't say disappears, it's still there, but the effects of the sun disappear. The stars come out, the birds will start to chirp, and for a couple minutes, it's like night in the middle of day. That's August 21st of next year. And since you guys have your calendars and you're putting them on your calendars, I want you to put Thursday of next week, Thursday of this week on your calendar. Thursday of this week, we will be seeing what we hope to be the most active Perseid meteor shower in several years. Every year, the Earth grazes through the trail of a comet, Comet Swift-Tuttle. We've been hitting that comet trail for hundreds of years, maybe thousands of years. And every time we hit it, tiny little pieces of rock, and I'm talking tiny, like sand, size of a fleck of sand. We hit that at really, really high speeds, tens of thousands of kilometers an hour. And when we do so, those flecks of rock fluoresce in our atmosphere. They heat up, they burn up, and they produce very bright streaks of light called meteors. And this Thursday night will be treated to, hopefully, a great show of the Perseid meteor shower. And if you do go outside after the sun sets and the sky starts to get dark, just look north. Look north and you should see some Perseids. I would also say that the Perseids are going to be nice this year. I've already seen some Perseids in my backyard this week. It's already started. And hopefully tonight we'll get a chance to see some Perseids as well. Okay. So, you've got this giant telescope. Telescope time on any very nice telescope is really expensive. On the telescope that Hubble used, it's 100 years old. It's still really big. They rent it out to groups that are interested. If you want to use the not the Hubble telescope, the telescope that Edwin Hubble used. If you'd like to borrow it for a night and point it at whatever you'd like and do observation, it will cost you $5,000. Imagine, I have no idea what it costs for the Hubble Space Telescope, but I will say that universities and science groups the world round are always bidding for time on the Hubble Space Telescope. And so when a large petition arrived on the director's desk to point the Hubble Space Telescope at a sky that had nothing in it for a really long time, it was laughed off. The idea was, hey, let's point it at nothing and spend a lot of time looking at nothing and see if there's something there. And so naturally, for many years, this was a project that was dustballed. But the petition grew so large and the argument for it so sincere and moving that they eventually relented. And they didn't do it in one shot. They picked a part of the sky that had nothing in it. And this is the part of the sky that I'm going to show you. They've actually done several of these, and I'm going to show you the most recent iteration of this. But they pick a small part of the sky. This is the size of the moon, again, to give you the idea of the size. And most people think the full moon is actually really large. So let me disabuse you of that notion right now. The full moon is smaller than your pinky fingernail held at arm's length. It just looks really big when you see it rising on the horizon for some psychological reasons. That little XDF square that is there is approximately the size of the eye of a needle held at arm's length. Say that again. You take a needle, you hold it at arm's length, and you close one eye and you look through it. That's what you're looking at. And so Hubble pointed at that for about 23 days over this. I mean, they did it in chunks, but the cumulative total is about 23 days, pointing at nothing. Expensive telescope time, pointing at nothing. What a ridiculous project. This is what they found. Where there's nothing, there were 5,500 galaxies. This image contains over 5,000 galaxies, each of them comprising hundreds of billions to trillions of stars. Where there's nothing. And most of those are spiral galaxies. So most of those stars in those galaxies have planets. We believe 5% of them have Earth-like planets. These are 3,000 separate images stacked on one another. 23 days worth of exposure time over a period of a decade. It's a testament to the pointing accuracy of the Hubble Space Telescope to be able to get that same spot that many times. Remarkable. Let me tell you what you're looking at. You're looking through time when you see this image. Because light takes time to get here, the further away the object is that's emitting the light, the longer it takes the light to get here. So when you see an image like this one, you're seeing different time periods. I'm going to pick the only spot that I can consistently find, that red streak there. When you see that little red streak, you're looking at a galaxy that's 9 billion light years away. That is light that is over 9 billion years old. So naturally that light is redshifted. It's been stretched by the expansion of space, so it's longer wavelengths, so it's a little redder. Maybe that's why this is red, I'm not entirely sure. But in this image, you're seeing sort of a stack of yearbooks for this part of the sky, dating back to 9 billion years. This is, in a way, a deep core sample of our universe. Much further, and you won't be able to see visible light, because we believe during the Big Bang, the first portion of the Big Bang, the first couple 100,000 years, we believe it wasn't opaque, I should say it wasn't transparent to light, it was opaque to light. And that at a certain point, around 300,000 years, light was able to move about. And after that, we had star formation. So these may very well be some of the early galaxies in our universe. So if you extrapolate this image across the sky, remember you're looking at just the eye of a needle. That's the size of the piece of the sky that you're looking at. If you extrapolate this across the entire sky, what you get is, for a 23-day exposure, access to 100 billion galaxies, each of them parent to hundreds of billions of stars. So, and most of them, nearly all of them, home to planets. You put that together, and in our observable universe, we believe there is 10 sextillion stars. That is 10 with 22 zeros after it. On a good day, we have access to 6,000 stars or so with our naked eye. On the best day, Hubble has access to 10 sextillion stars. And this is the extreme deep field image of Hubble. And I have a really hard time doing anything after I see this image. Every time it does it to me. Questions? By the way, there's that red streak I told you about right there. Yes? Yeah. Their pointing accuracy, if I understand right, is the width of a human hair seen from a mile. That's how accurate they have that telescope to be able to point at that stuff. It is remarkable. I'll go one further and tell you what I think is more incredible about this image. If you accept the idea that you're made up of stuff in the universe, the stuff in the universe, your body is comprised of old stars that have blown themselves apart and stuff. If you accept those ideas and you realize what you're looking at this image of the universe, but you are, in a sense, the universe expressing itself as a human for a little while. That's what Eckhart Tolle says. this is the universe. When you look at this, the universe is looking at itself. This, to me, I always think of this as I'm pondering the universe, but in a very real way, it's the universe self-reflecting when you're thinking about this stuff. Are there any other questions? All right. I think the sun goes down in a few minutes. We'll meet out at the spot between those sidewalks near the exit. I'll have a telescope out there. We'll do the old-fashioned thing. How many of you guys have actually watched the stars come out? This used to be evening television for our ancestors. We're going to go watch the stars come out. As the things come out, I'll tell you what we're seeing, and we'll point the telescope at them, and we'll take a look. So thank you, and I'll see you guys outside.